Let us continue our discussion on dynamic programming. Quick recap of how dynamic programming is positioned with other algorithm design strategies. We saw that decrease and conquer or its close cousin, divide and conquer, or at one end of the spectrum of design strategies. At the other extreme end, we have exhaustive search, an example of which was enumerative search, roughly what we called brute force. In between, we have DP. Typically, this is big O of a polynomial such as n squared or big O of n log n or something like that. Exhaustive search or enumerative search is often exponential. And DP in between is again polynomial, n squared or big O of n cubed and so on. In decrease and conquer and divide and conquer, we have one or a few subproblems. In exhaustive search, we have a number of subproblems. If we consider the whole process, a number of subproblems are overlapping. They are solved again and again. We identify those overlapping subproblems. Those subproblems which are solved more than once and get rid of that duplication, resulting in DP. So there is a relationship between exhaustive search and DP. We also saw that the main idea behind DP is solve a subproblem only once and store its solution in a table, in a cache. Second time or third time or any subsequent time we encounter the subproblem, do not solve it but retrieve it from the table. So solve a subproblem only once and store it in a table. Every subsequent need to solve the problem, we do not actually solve it, we only retrieve the solution. Thus, there is a trade-off between computing solution to the subproblem versus storing and retrieving a solution to the subproblem. Do not compute solution to every subproblem, but wherever possible, store it and retrieve solution to the subproblem. Dynamic programming strategy is particularly useful and effective in problems involving sequences. Some of the Classical problems are longest increasing subsequence, longest common sequence, edit distance, and so on. In this class, we will illustrate how DP, dynamic programming, is used effectively in problems involving sequences. We will solve only one problem, but that will give you an idea how useful, how effective DP is in dealing with sequences. Because of its usefulness or effectiveness in solving problem involving sequences and subsequences, dynamic programming has found to be one of the very popular design strategy in bioinformatics. Where we need to process genes and DNA sequences. DNA is, after all, it's a sequence of symbols. Okay. And after discussing about dynamic programming strategy, these are the steps that we came up with. In order to solve a problem using dynamic programming, very often, most often, we follow these steps. 1. Identify the subproblems. This is a creative work. It is not a mechanical, automatic work. Once we have identified or we have an idea how to deconstruct a given problem into subproblems, we have to find a recurrence relation, a recursive definition between a subproblem and the smaller subproblems required to be solved. I do not count these two steps as one and the same step. They are related. Identifying the subproblems. Given a problem, what are the possible ways in which I can reduce or divide or deconstruct the given problem into a subproblem is done very intuitively and informally. Whereas a recurrence relation is a formal description between a subproblem and the smaller subproblems. In order to solve the given subproblem, we need to first solve the smaller subproblems. The solution to the given subproblem can be constructed only from solutions to the smaller subproblems. When we write a recurrence relation, we also identify the variables of recursion. It may be a recurrence relation involving only one variable or two variables or even three variables. We will see examples of each of these. Also, we know that every recurrence relation or recursive definition should also have base cases or boundary cases. Step 3 is optional. After we have identified the subproblems and formalized the recurrence relation between a subproblem and the smaller subproblems on which it depends, it is possible to immediately write an exhaustive search algorithm. It is optional. We don't need to write that. But without further ado, we can translate the recurrence relation into an exhaustive search. And if you trace the exhaustive search process, we will also recognize there are overlapping subproblems. The same subproblem is solved again and again. The subproblem is the same, only that there is a number of instances of the same subproblem solved or duplication. But this is not strictly speaking necessary. So once we have the recurrence relation and identified the variables of recursion, we have to design the table to store solutions to the subproblems. Sometimes we tend to think that dynamic programming is all about filling entries in a table. It is not that. Without the first two steps, identifying the subproblems and how using a recurrence relation from the solutions to smaller subproblems, solution to a larger subproblem can be constructed. It is vain to design a table. But once we have done the first two steps, we have to design a table. Whenever we solve a subproblem, we have decided to store its solution in the table. It may be a one-dimensional table or simply an array, or it may be a two-dimensional table, or it may be a three-dimensional table. Sometimes, other than table, even though we call it a table, we may even use a tree structure to store the solution. Not very often, but sometimes. So table is a very general data structure. Strictly speaking, I should use the word cache. A memory where I can store the solutions to all the subproblems. Okay. Once we have a table, we need to think about in which order the table entries will be filled in. If it is 1D table, from left to right, or from right to left, or from 1 to n, or from n to 1. If it is a 2D table, some of the popular filling strategies are row major order, or column major order, or even diagonal major order. So the order in which the table is filled depends on the ordering among the subproblems. Order the subproblems so that smaller subproblems are solved before the larger subproblems. This property, it should be possible to arrange sequences of problems in this way. Whenever we come to solve a subproblem, by then all the smaller subproblems which are required to have been solved are already solved. I stated this property of the problem by a DAG, directed acyclic graph. If we represent the relationship among the subproblems, it is a directed acyclic graph. The dependency is all in one direction. There is no dependency in the opposite direction. We will never come across a situation where this subproblem, let's say Pi, is needed for Pi plus 1, which is needed for Pi plus 2, and so on. And we will never come across a situation where Pi plus 2 is needed for Pi. This will never happen. This is wrong. Once we have taken the first 5 steps, then we write the algorithm and finally analyze the running time of the algorithm. So if all we do is write the algorithm, it is of no use. Now let us go on to the problem. Consider the sequence 5, 2, 8, 6, 3, 6, 9, 7. If we remove any of the elements of the sequence, the result is a subsequence. For example, if we remove 5, 8, 6, 8, 6, 7, the result is 2, 3, 6, 9. It is a subsequence. You should note the difference between a subsequence and a substring. In a substring, the elements are consecutive in the original sequence. In a subsequence, the elements need not be consecutive or contiguous in the original sequence. For example, 6, 3, 6, 9 is a substring. But 6, 6, 9 is not a substring, it is a subsequence. So distinguish between the two words substring and subsequence. 5, 8, 9 is another subsequence. So what is the problem? The input is a sequence of elements A, which is equal to A0, A1. Okay, I think In the algorithm, I use A1, A2, and so on, AN. The subsequence of A is another sequence obtained from A by deleting 0 or more elements without changing the order. Of the remaining elements. We are interested in an output which is the longest subsequence whose elements are in strictly increasing order. Two, 3, 6, 9 is an increasing subsequence. 9 is larger than 6, which is larger than 3, which is larger than 2. 5, 8, 9 is also an increasing subsequence. 9 is larger than 8, 8 is larger than 5. It is possible to come up with a number of increasing subsequences. Out of all the increasing subsequences possible, find the longest increasing subsequence. For example, here in 5, 2, 8, 6, 3, 6, 9, 7, a longest increasing subsequence is 2, 3, 6, 9. 2, 3, 6, 9 is indeed a longest increasing subsequence. 2, 3, 6, 7 is also 2, 3, 6, 7 is also a longest increasing subsequence. 5, 8, 9 is not a longest increasing subsequence because length of 5, 8, 9 is 3, whereas length of 2, 3, 6, 9 is 4. 2, 3, 9 is an increasing subsequence, but it is not a longest increasing subsequence. At this point, I want to ask you a question. We want to solve this problem. Okay. Let me simplify the problem slightly. Instead of longest increasing subsequence, which I abbreviated LIS because I need to repeat the word often. Let me say I am interested only in the length of the longest increasing subsequence. The output need not be 2, 3, 6, 9. It is enough if the output is only 4. Out of all possible subsequences of the input sequence, the length of the longest increasing subsequence, the length of the LIS is 4. We will solve the simpler version, the easier version of the problem first. But ultimately, we may be interested in the longest increasing subsequence, but that would be part 2. Part 1 is input is a sequence, output is the length of the longest increasing subsequence. Let me stop here and ask you a question. Can you come up with an idea to reduce the problem into a subproblem? How will you deconstruct? Can you suggest an idea to deconstruct the problem into a subproblem? If I can solve the subproblem, I can construct a solution to the given problem. In this way, can you come up with a subproblem? For example, if I am given the sequence 5, 2, 8, 6, 3, 6, 9, 7. If I know the LIS of 5, 2, 8, 6, 3, 9, 3, 6, 9, from that, I can find the LIS of the whole sequence. Is that possible? Or if I can find out the LIS of 2, 8, 6, 3, 6, 9, 7, from that I can find out the LIS of the whole sequence. When I suggest this idea, actually what I am doing is reduce a problem of size n, reduce a sequence of size n, length n, to a sequence of length n minus 1. Find the LIS of the sequence of length n minus 1. From that, you can find the LIS of the given sequence, which is of length n. Will this idea work? This is how you work in array-related problems. Find the maximum of an array. How do you solve? Find the maximum of an array of n numbers. you reduce it to a subarray of size n minus 1, the first n minus 1 numbers. Find the maximum of a subarray of size n minus 1. From that solution and the nth element, I can find out the maximum of the whole array. Like that, can you suggest an idea to deconstruct the problem into a subproblem?
Sir,
yeah.
Selecting an element can be a yes or no question. It's similar to an yes or no question, like selecting
Correct.
5 or not selecting 5. So,
Correct.
If I select 5, I should add it to my subsequence, or else I'll move to the next element and then I'll add it to my subsequence. Subsequently, yeah. I'll be reducing the space and I'll take out the maximum length from the subsequences.
I more or less follow your argument. Therefore, what is your suggestion for the subproblem?
Yes, sir. Like selecting one or leaving it and selecting or leaving the next one, sir. Like reducing the total size.
So, how many subproblems you have then?
2 subproblems, sir. Like selecting the element, selecting the first element or leaving it.
Okay. So, what's the name?
Sarvesh, sir.
Okay. So, Sarvesh suggests find the LIS of 2863697. Then 5 may be either a part of the final LIS or 5 may not be a part of the final LIS. It is his suggestion. So there are 2 subproblems. Is that right? His suggestion is 2 subproblems. Okay, let us go on. Identify the subproblems. Let L of I be the length of the LIS of ai to n. Suppose this is ai to n, I plus 1, I plus 2 and so on up to n. That starts with a at I. In this example, suppose what is the longest increasing subsequence that starts with 5? What are the subproblems? If I simplistically assume find the LIS that starts with LIS of the subsequent subarray 2863697. Okay, once you have found out the LIS of the subproblem, then we can decide about including 5 or not including 5. That may work or may not work. The moment I have a doubt it may not work, then I have to consider exhaustive search. Okay. Suppose 5 is a part of the LIS, the longest increasing subsequence. What are the possibilities that may follow 5? 5 may be followed by 8 in the LIS. But 5 can never be followed by 2 because it is an increasing subsequence. Using this idea, I will say 5 cannot be followed by 2, but 5 can be followed by 8. 5 can be followed by 6. 5 cannot be followed by 3. 5 can be followed by 6. 5 can be followed by 9. 5 can be followed by 7. So what I would do is, okay, what is the length of the LIS that starts with 8? What is the length of the LIS that starts with 6? What is the length of the LIS that starts with this 6? These are 2 different 6s. What is the length of the LIS that starts with 9? What is the length of the LIS that starts with 7? Out of all these 5 LISs, which one is the longest? To that, I would prepend 5. So the longest increasing subsequence, LIS that starts with 5 is simply the maximum of the 5 LISs plus 1 if I am interested only in the length. So how many subproblems I have? 1, 2, 3, 4, 5. I have 5 subproblems. Solve all these 5 subproblems. Take the maximum of the 5 values, then add 1. That is the length of the LIS. Even though I write LIS, actually we are interested only in the length of the LIS. So to solve LIS that start with this 5, I am saying find the LIS that starts with 8, find the LIS that starts with 6, find the LIS that starts with this 6, find the LIS that starts with this 9, find the LIS that starts with 7, take the longest LIS, add 1. That is the LIS, length of the LIS starts with 5. Look at that. We have not used decrease and conquer. We have used exhaustive search. Solve every sub-problem. 5 may be followed by 8 or may be followed by 6 or 5 may be followed by 6. So in every possible way, I have deconstructed the given problem into a sub-problem. We have exhaustively considered all the sub-problems. Okay, so every LIS in AI plus 1 to n that starts with an item larger than AI can be extended with AI, A at I. Therefore, every LIS, longest increasing subsequence, that starts with an item larger than AI is a suitable subproblem. This is very important because this idea cannot be mechanically, automatically created. With some flair and experience, we have to come up with an idea. We are not solving one subproblem. We are solving a collection, a set of subproblems. In fact, an exhaustive set of subproblems. There is no other way in which 5 can be prepended to an LIS. We are considering every LIS to which 5 can be prepended and take the longest one. Let items at J1, J2, J3 be larger than A at I, as I have shown in the diagram. There is a number of items, but only J1, J2, J3, J4, J5 items at these indices are larger than item at AI. Therefore, I can write length of the LIS that starts with I is consider length of LIS that starts at J1, length of LIS starting at J2, length of LIS starting at J3, and so on. Consider the maximum, take the maximum and add 1. Why add 1? Because we have to add the element I itself. If you write a little neatly, it will be L of I is equal to, consider all LJs so that J is larger than I and A at J is larger than AI. Only those elements which are larger than ith element need to be considered. Only larger elements can follow this ith element. Smaller elements cannot follow. Out of all those, take the maximum. So we come to the second step of DP, recurrence relation. L of I is expressed in terms of L of J. This is a larger subproblem. This is a smaller subproblem. A number of smaller subproblems. L of J for all J larger than I and the jth item, the jth element is larger than ith element plus 1. What are the boundary cases? So the recurrence is returned on only one variable I. What are the boundary cases? What is L of n in the given example? What is the longest increasing subsequence that starts at 7? Just 1. Because 7 cannot be followed by any element. Similarly, what is the longest increasing subsequence that starts at 9? Since no element to its right is larger than 9, it is 1. So they are the base cases. L of n is equal to 1. L of I is also equal to 1 if all elements to the right of I are smaller than ith element. Okay. So this is the second step. First step, identify the subproblems. Second step, write the recurrence relation. From the recurrence relation, we can find out the recursion is on one variable or two variables or more, and also the base cases. At this point, we can write an exhaustive search algorithm, but this is only optional. We don't need to do that unless we are asked We don't need to do that. Algorithm, length of the LIS that starts at ith element. Input is the start index I. Output L of I is the length of the LIS that starts at the ith element. It's a straightforward translation of the recurrence relation. Okay. For j becomes I plus 1 to n, we are considering I plus 1, I plus 2, and so on, n. Out of all the elements to the right, we are interested only in those elements, jth element, this is j, which are larger. And we are interested in the longest increasing subsequence, length of the LIS. How do you find out? Best, I am using this as a maximum operator, very informally. This is a non-standard notation. Compare best and L of j, whichever is larger, that becomes the new best. We have initialized, therefore we have initialized best to 0. And the final answer is, it is simply not L at the longest L, the largest L, it is the largest L plus 1. Because we wrote L at I is 1 plus maximum of all Lj for j greater than I, such that the jth element is larger than the ith element. Okay, so this 1 plus is what we do here. Very simple. We have solved the problem. The recurrence was blindly, simplistically translated into an exhaustive search algorithm. What is wrong with this algorithm? Suppose, by the way, this calculates the length of the LIS of LIS. We are interested in L of 1. In fact, we are interested in L of 1, L of 2, L of 3, and so on, L of all the way to L of n. Out of all these, which is the largest, we have to take. But there is a shortcut. What we can do is, we have 1, 2, 3, 4, and so on, n. Put the element minus infinity. If there were no this, we have to find out what is, the first item may, the LIS may start with the first item, or the LIS may start with second item, or the LIS may start with third item. We do not know. Therefore, we have to find out the LIS of all LISs. LISs which start with 1, LIS that starts with 2, and so on. But synthetically, in the 0th position, let me put minus infinity. Then I know the LIS has to start with minus infinity. So A at 0 becomes minus infinity. In that case, it is enough to find out L of 0. What is the length of the LIS that starts at 0? But since I have added a new element to from the result, subtract 1, that is a result. That is the actual result. Suppose 10, 15, 20, 25, and so on, 30. What is the LIS? The LIS will be minus infinity, 10, 15, 20, 30, 25, 30. How will the exhaustive search algorithm work? Suppose we have, this is 5. L of 0 will call L of 1. This is to calculate L of 1, it will consider all the elements to the right which are larger than the first item. In this particular example, 15, 20, 25, 30, all are larger than 10. Therefore, calling L of 1 will result in calling L of 2, L of 3, L of 4, L of 5. Calling L of 2 will result in calling L of 3, L of 4, L of 5. Calling L of 3 will result in calling L of 4, L of 5 because of the nature of the problem. The elements are already in sorted order. Calling L of 4 results in L of 5 and so on. It is easy to see that several subproblems are duplicated. For example, L of 5, 1, 2, 3, 4, 5, 6, 7, 8. There is only one subproblem, but it is solved 8 times. If we consider 4, L of 4, first time, second time, third time, fourth time. One subproblem, but 4 instances. We consider 3, L of 3, L of 3, 2 times. So L of 4 is an example of an overlapping subproblem. What is the meaning of overlapping? L of 4 is required for solving L of 3. L of 4 is also required for solving L of 2. L of 4 is again required for solving L of 1. This is an example for overlapping subproblem. This is what we mean by overlapping. The same smaller subproblem is solved repeatedly, duplicated to solve different larger subproblems. By the way, I said this exhaustive search and seeing the overlapping subproblem is not needed. Okay. Graphically, we can show these subproblems and the dependencies. For example, for 5, we have to solve the subproblem that starts with 8 or 6 or 6 or 9 or 7. For solving the subproblem that starts with 2, we have to solve subproblem that starts with 8, that starts with 6, 3, 6, 9, 7. To solve the subproblem that starts with 8, we need to solve only subproblem that starts with 9. So it is possible to order or arrange the subproblems in such a way that the dependencies are all in one direction. You do not see arrows in the opposite direction at all. And let's come to the next step of the problem solving. Table and order of filling. Since we recurse on only one variable I, a 1D table is enough. This is all the table we need. This is the index 1, 2, 3, 4, 5, 6, 7, 8. These are the elements in the input table. This is input. This is the subproblem solution table. We have artificially inserted this minus infinity so that it is enough to find out L of 0. Okay, so the subproblems are L of 0, L of 1, L of 2, L of 3, L of 4, L of 5. In which order we have to solve the problem?
L of 5 first, sir.
Yeah. because if after we have solved L of 5, we can solve L of 4. After we have solved L of 4 and L of 5, we can solve L of 3. Okay. Therefore, if you want to order, we have to order in this way. L at 5 should be solved. L at 4 should be solved. Then L at 3 should be solved. L at 2 should be solved. Oh, by this I don't mean, and finally L at 0. But by this I don't mean L at 2 needs only L at 3. I mean to solve L at 2, whatever smaller subproblems are needed, they are already solved. L at 5, L at 4, L at 3. We may use all of them or only some of them. To solve the subproblem L at 1, whatever we need, L at 2, L at 3, L at 4, L at 5, they have already been solved. We may use only a small set of a subset of the subproblems. Okay. Therefore, this table will be filled from right to left. Here is the algorithm. Algorithm, longest increasing subsequence, array A 1 to n. Input is an array A 1 to n. Output length of the LIS in A. Artificially, we have inserted A at 0 is equal to sort. This is minus infinity. Typo. So what should we do? We have to fill in solutions in the table. There is a table L from right to left. Therefore, for I becomes n to 0. First n, then n minus 1, then n minus 2, and so on. 3, 2, 1, 0. L at I is equal to 1 to start with. And then consider this. Suppose this is L at I, this is I plus 1, I plus 2, and so on, n. How do we solve problem I? We are interested in finding out L at I. Consider for j becomes I plus 1 to n. Consider I plus 1, I plus 2, and so on. We have already the entries for them. They have already been filled. Okay. And out of all these subproblems, we are interested only in those subproblems for which A at j is larger than ai. So for each of I plus 1, I plus 2, I plus 3, and so on n, if that A at j is larger than A at I, okay, then we are finding out the maximum. Compare L at I versus 1 plus L at j. I mean, I with, for example, L at I is something. This is L at, suppose A at I plus 2 is larger. Compare these two things. This one is necessary. Whichever is larger, there is a new value of Li. Basically, what we are finding out here is maximum A I plus 1 j plus 1. Only that it is not simply finding out what is the maximum value in the subarray I plus 1 to n, but maximum value in the subarray I plus 1 to n, but consider only those elements which are larger than I, and therefore I do not use this notation. Be careful. In one sense, this algorithm, what does the algorithm does? It finds out the maximum of all the maximum of the subarray I plus 1. I mean, subarray is L at I plus 1 to n. But when doing so, do not consider all the items of L at I plus 1 to n, but only those elements which are larger than L at I. And finally, return L at 0. The subproblem that we are interested in is L at 0. So we have solved L at n, L at n minus 1, L at n minus 2, L at 3, L at 2, L at 1, L at 0. L at 0 is the subproblem that we are interested. It is 1 longer than needed, and therefore we subtract minus 1. Now let us analyze the running time. Okay, what is the difference between this dynamic programming algorithm and the exhaustive search algorithm? The difference in exhaustive search, there were duplicate, okay, the subproblems were solved redundantly. One subproblem may have been solved, may have been duplicated and solved a number of times. Whereas in DP, every subproblem is solved only once. We are not solving any duplicate subproblem. There is no redundancy in computing the solution. First time we compute the solution of a subproblem, we store it in a table such as L. Subsequently, we are not, to emphasize the difference, note that L at I. This is store and lookup for solution in a table, then bracket notation. Whereas here, call to solve a subproblem. So L of I means we are computing the solution. L at I means we are looking up for the solution. Okay. So that's the main difference. Now for computing analyzing the running time, the innermost loop takes constant amount of work. This is the innermost loop body. I varies from n to 0, j varies from I plus 1 to n and 1. Therefore, the running time is this. I varies from n to 0, j varies from I plus 1 to n 1. And this would be, you may say, n minus I plus 1 plus 1, which is n minus I minus 1 plus 1, which is n minus I. That is one way of writing. Another way of writing, maybe you can rewrite this as for j is equal to 1 to n minus 1 for j is equal to 1 to I. Okay. Sum of 1 from j is equal to 1 to n will be n. Sum of 1 for j is equal to 1 to I will be I, in whichever way you write. So that is n minus I. Sum of n minus I for I is equal to n to 0. Separate this. Sum of n minus sum of I. N is a constant. Therefore, you can take that out. Therefore, this is sum of 1 for I is equal to n to 0. There are n plus 1 terms. Therefore, this is n times n plus 1. Whereas here, this is 0 plus 1 plus 2 plus and so on up to n. Therefore, this is n times n plus 1 by 2. N plus 1 is common. N minus n by 2 is n by 2. Therefore, this is n times n plus 1 by 2. So, this is n squared by 2 plus n by 2. We have big O of n squared. In fact, you can even write this as big theta of n squared. All right. There is a little more problem left, but I will not explain that. I will just leave it to you. What we have calculated now is only the length of the LIS. Suppose I am interested not merely in the length of the longest increasing subsequence, but in the subsequence itself. Then you have to slightly change the problem. In addition to maintaining a length array, we should also maintain a successor array. As we are calculating the length of what is the length of the LIS starting at I, we should also calculate what is the successor for I. And here we have to update the successor. So if you want to retrieve or reconstruct the actual longest increasing subsequence and not merely the length of the LIS, we have to maintain one other state variable, the successor array. Look at the algorithm on the left side. I have copied, pasted the original algorithm and added this. S at J. Oh, this is not J. This is I. This is I. Formally initialize L at I becomes 1. Now I have initialized L at I with 0. And finally I am updating it, incrementing it by 1. So it's all okay. To start with, I say there is no successor for I. Only after I have found out the longest increasing subsequence, the length of the LIS, I will have a successor for I. So here is the change. If jth item is larger than ith item and length of the LIS starting at j is greater than length of the LIS starting at I, then we have to update what is the length of the LIS. We should also update the successor. Okay? This is the only change in the algorithm. Now, this is the algorithm for reconstructing. I am not explaining that. I leave it as homework. Reconstruct the LIS itself. We are almost done. A related problem is this. What we have just now considered is the longest increasing subsequence. There are several different ways we can define similarity between two strings. Suppose we have a sequence A at 1 to m and B at 1 to m, n to n. We have already defined the word subsequence. Remove 0 or more elements from A, you get a subsequence of A. Remove 0 or more elements from B, you get a subsequence of B. We are interested in finding out a common subsequence. At that, the longest common subsequence. A common subsequence of A and B is another sequence that is a subsequence of both A and B. A common subsequence is in both A and B. Describe an efficient algorithm to compute the length of the longest common subsequence of A and B. If we have solved the longest increasing subsequence, now we have enough understanding to solve this problem. Whereas LIS recurs on one variable, let me call this LCS, longest common subsequence. LCS will recurs on two variables, L of I comma j. You may say, okay, this is A, this is B, suppose 1 to I minus 1 or 1 to I and 1 to j. We have already found out the common subsequence. Okay. Find out the common subsequence between I to m, I plus j plus 1 to n, something like that. That's one homework. Another very important problem. The edit distance between two strings is the minimum number of letter insertions, letter deletions, letter substitutions required to transform one string to another. For example, I want to transform food to money. You can do any of these three operations: insert or delete or change. Look at that. F is changed to M. So food becomes moved. Then O is changed to N. It becomes MOND. Then I insert here E. We get MONED. Then I change D to Y. So in 4 operations, I can transform FOOD to MONEY. Therefore, I say the distance between food and money is 4. This is not the only way. By a combination of changes, insertions and deletions, it is possible to transform one string to another string. What is the minimum number of such operations needed to transform one string to another is called edit distance. If you have solved the longest common subsequence, solving the problem edit distance becomes easier. Okay. For tomorrow's lab, the main problem is edit distance. It's a standard problem. If you look up the net, you will even get solution in Python. Therefore, let us not congratulate ourselves if we solve the problem. If you understand the problem, write on your own, then there is some value in solving the problem. A few other exercises, these are in connection with, not related to these, simple problems. You are given a grid of points in XY plane. In a staircase path, every step is either forward or upward, to the right or to up. Never step backward or downward. Count the number of staircase paths from the bottom left corner here to the top right corner here. In how many different ways we can reach from 0, 0 to 8, 5? Design an exhaustive search algorithm. I have shown you one path. Design an exhaustive search algorithm. Let there be m horizontal steps and n vertical steps. Enumerate all possible permutations of m plus n steps. Design an algorithm using dynamic programming. In fact, this could be solved using combinatorics. You don't even need an algorithm. But write a DP algorithm. Another variant. A fisherman is in a rectangular area. The value of the fish at point ij in the sea is specified by an n by m 2D array. A. Write a program that computes the maximum value of fish a fisherman can catch on a path from upper leftmost point to the lower rightmost point. The fisherman can only move down or to the right.